got Vincent.
I mean, it's not peculiar only to you guys, but it's actually very common.
Vincent,
I've taught different places.
Evident.
You know, I mean, it's a common thing, but you do know that when you go out and work, you don't want to put down the account number. Because if you put down the account number, your supervisor pick it up. What's your efficiency factor? 27.
Can
You
loan
know,
out
you are what kind of
in the
admin
guild.
is that? You know, I mean, then the first thing is say, what? UOG student. You can imagine. So it's very important. Whatever you all do, that's what we basically we trying to stress over and over again. Right? Not only I want you to get the number correct, I also want you to be very careful a lot of the time whether the number actually makes sense or not. Right? So you are the engineer. So you need to basically make the you need to make a decision, right? Whether the number makes sense. If this number makes sense, yes, I'll use it. If this number doesn't make sense, right, fine. It doesn't make sense, I go back and I check. Right? If I can't, I go back and check to see where did I make mistake and so on. Okay, so actually that's important. Alright, coming back, your proportion again, as we mentioned, used to control your steady state error, right? We did mention. And then the derivative gain to control the speed of the response, you can actually use it in a sense that in this case here, if you look at your time constant, your overall time constant count is actually set at 1 second. Right? In your closed loop, it becomes 0.2 if you were to use just Kp equal to 4. Right? Kp is equal to 4, 1 over 4 plus 1 is 5, 1/5 is 0.2. But if you were to use a PD controller, you can see that, well, actually, we do reduce the closed loop transfer function, the time constant, a little bit because of the KD term. So KD term here, we use 1 for illustration purpose, right? But typically, you use a very small KD term. In this case, also in the P controller and PD controller, for first order system, you do not see much of the benefit because first order system, first, you don't have any oscillatory effect. As we mentioned, your PD controller, the major effect for your PD controller is to deal with second order oscillatory effect. It has an effect of trying to improve your damping. Okay, so remember this. PD, what you want to do, you basically want to improve your damping. So when system has a very low damping, PD has a direct effect of improving your damping. Okay, so this is supposed to be last week. So now we finish what we need to discuss last week. Then we'll go on to take a look today. Continue from last week. Steady state generic form of your second order transfer function. So if I have to do this for your second order transfer function, right? If I use it to represent the second order system, you can see that the DC gain is 1. So of course, when you put unit step input, you have no steady state error. But in the real life, when you need to model the system, it all depends on what kind of system that you're modeling. Okay, the system that you're modeling, sometimes it ends up something like this. Sometimes you don't even have the numerator. So as a result, open loop, you already see error. Okay, so don't say that, hey, how come the open loop transfer function already so nice, then you put in a P controller, and then you ended up you're trying to tweak the P controller to reduce the steady state error. Okay, but that is a very generic form of representing your first order, second order system. Okay, in the open loop. Right? So if you have to use this as an open loop transfer function, of course the DC gain is 1, and there's no steady state error. Okay, but now what the whole objective here is we use the most generic, then we analyze it. The thing that we want to achieve is to see how various different types of controller can actually help us to solve the problem that we face. Okay? Alright, in this case here, you will see that we are still doing the same thing. Your closed loop transfer function and the error transfer function, you're given these two, CS over RS, ES over RS. Okay? So, key thing, as I mentioned, if you were to try to work it out, what will be your DC gain? Your DC gain is going to be equal to, again, Kp divided by Kp plus 1, because your omega n squared all cancel out. So you can actually see that in our system here, when you close the loop, even the second order system, right, it doesn't matter what kind of damping, what kind of undamped natural frequency. Your DC gain is always Kp over Kp plus 1. Okay, and you can see that the effects and so on. So CSS, as we put it, Kp over Kp plus 1, and of course, what will be your steady state error? 1 over Kp plus 1, right? Your steady state error when you work it out. So again, if you were to ask me this one I cut and paste from the section 6. Your notes from section 6 and all that, I just basically use it. So if you want, of course, you need to verify it. So this is a case, a very generic form, assuming a second order underdamped system. So you have a exponential term. Okay, exponential term basically giving you the damping effect. You also have the oscillatory form, right? Your oscillatory will be your cosine and your sine. Okay, so from here, of course, what we're trying to work out is what will be your closed loop damped natural frequency. Okay, so I mean, one of the things that I guess Glasgow actually stressed quite a fair bit is basically to look at what is a damped closed loop natural frequency. So you do know that your omega d is actually worked out based on your omega n and your zeta. So omega d is equal to omega n multiplied by square root of 1 minus zeta squared. Okay, so but in this case here, you need to basically go back to your this transfer function. Because why? In this case here, what is the omega n? Omega n is going to be square root of Kp plus 1 omega n squared. So your omega n, your closed loop omega n has actually changed. And then what about your closed loop damping? So you need to actually work it out, because we do know that in your closed loop, your zeta closed loop, 2 zeta closed loop, omega n closed loop is going to be equal to this term. Okay, but you have already changed your closed loop, so you can actually try to relate them, and that is how you see that will be your then closed loop and then natural frequency. I mean your then closed loop natural frequency, sorry. Okay, so introducing your proportional gain creates steady state error and also increases frequency, in the sense that you can actually see that this actually has increased, right? Because why? Because this is your omega n, and then here what happened now is your omega d is going to be greater compared to your original omega d, correct? Because of the Kp term. If I set Kp equal to 10, so originally, what is your omega d open loop? Omega d open loop is going to be equal to omega n multiplied by square root of 1 minus zeta squared. But now Kp is equal to 10, so it's 11 minus zeta squared. So it will be a larger value for your omega d. And that is why we say, introducing your proportional gain, you create steady state error. At the same time, also increases the frequency. So this is one example that we can actually take a look. In this example here, overload damping ratio to natural frequency given omega n is 5 radian per second, zeta is 0.2. Response is very oscillatory, as you can actually see okay. So this one is basically, this solid line is plotted using omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. That open loop. So that is why you see a steady state is 1. Okay. Subsequently, you have a proportional controller. You put it in, Kp is equal to 1. Kp is actually equal to 10. Okay. So you do see, you can actually compare what happened when Kp is equal to 1. What happened? Kp is equal to 1 at the lower level. You have a larger steady state error. Alright? Because what is your steady state value? Kp over Kp plus 1. So Kp over Kp plus 1, if Kp is equal to 1, what is the steady state value? Half. Steady state error 0.5. Okay, so from here you can actually see that this will give you half the steady state error. But when you increase your Kp to 10, what happened? Steady state is 1 over 11. So error is going to be what? Error is going to be less, right? Error is going to be 1 over 11 because Kp over Kp plus 1, steady state value is 10 over 11. So you can actually see that is actually this dashed line. But what happened, as we have mentioned just now, when you increase your Kp, you are increasing your frequency. When you're increasing the frequency, what happens is you see the response is actually more oscillatory. Okay, you look at the response. The response now versus the lower Kp, response is actually much more oscillatory. Okay, so there is a trade-off. There is a trade-off. If you want the response to be less oscillatory, then perhaps, you should use a smaller Kp value. If you use a large Kp value, this is a case where you see the response become more and more oscillatory. Okay, so this is the case in the open loop. If you were to carry out some of the calculations, you do know that because omega n is 5 radians per second, your zeta is equal to 0.2, so when you work it out, your omega d is 4.899. Kp is equal to 1, your omega d closed loop is 7 radian, your Kp is equal to 10, your omega d closed loop is 16.55, and that is why that correlates to when you see the response, they become more and more oscillatory, though you can actually try to reduce your steady state error. Okay? Alright, let's take a look at this work example here. You have a plant with a transfer function Gs is controlled by a controller of variable proportional gain Kp and unity negative feedback. Okay? So you have this. Okay, you have a Kp. Yes, let me take a look. What's wrong with this? Focus or autofocus? Don't like your. How come like that? unit step input. Okay, we are asked to show that the value of your KP actually has no inference and all that. Okay, so what happened here is you need to work out what is your CS over your RS. So what I'll do is I'll just write down the answer. Okay, you have to work it out. Okay, you have to work it out. Alright, so for unit step, RS is equal to 1 over S. Alright, so what is your CS? CS is going to be equal to 1 divided by Kp divided by S to the power 4 plus 1.2 S cubed plus S squared plus Kps. Alright, and then you need to find out your steady state value, your CSS. So what is your CSS? CSS basically is limit of S going to 0 as multiplied by CS. Okay, so in this case here, when you multiply out, it's going to be limit of S going to 0, you take away, so eventually you go back to Kp, S cubed plus 1.2 S squared plus S plus Kp, and it's going to be equal to Kp divided by Kp is equal to 1. And you can basically conclude that based on this, it doesn't matter what Kp value that you're using. It has no effect at all. Okay, it has no effect at all. That means your Kp doesn't actually affect your response. So from here, if you were to use a DC gain, what's the DC gain? Kp divided by Kp is equal to 1. So, you know, I mean straight away you really know. When you work out the closed loop transfer function without doing anything, you can really say that I know it doesn't have any effect because why? The DC gain is equal to 1. Right? And the DC gain calculation independent of your Kp value. Right? No matter what Kp value you pick, I'm always equal to 1. So I don't have any Kp in this case here. Okay? We basically show, okay or not, first part, right? First part, basically we were asked to show that the value of the proportional gain has no influence on the steady state value of the response of the plant to a unit step. And now we are asked, what is the effect on the stability of the system of a negative value of Kp in valuing the stability of the system for the value? So in this case here, we were asked to study the effect on the stability of the system of a negative value of your Kp. That means if Kp is actually less than 0, what happens? So go back, what is your closed loop characteristic equation? Your closed loop characteristic equation is going to be equal to S cubed plus 1.2 S squared plus S plus Kp equal to 0. Okay? Your necessary condition require that all coefficient present. So coefficient present, coefficient present, coefficient present, coefficient present. And also necessary condition requires that all coefficients must be of the same sign. Okay? So this is positive, positive, positive. Kp must also be positive. So what is the effect on the stability of the system of a negative value of Kp? That means when Kp is negative, what can we say? I taught you, right? The system at most marginally stable. Alright? We mentioned when you have one of the coefficient missing or negative, in this case here, actually you can actually say that system unstable. Okay? When you have at most marginally stable if you have 0 element. Right? We mentioned when we look at your 0 element, we say that, okay, what can we actually conclude when you have a 0 element? At most marginally stable. That means the system basically cannot be stable. But if you have Kp to be the negative sign, you can straight away say that system unstable. Okay, so this is actually okay to infer. System basically unstable because why? Because your coefficient, you have one of them basically opposite sign. Okay, and then they ask you to investigate Kp is equal to 1, Kp is equal to 1.5. Okay, alright. So we just do it, just to do it a little bit. I'll leave it to you to practice. And then because I believe that you can do it better than me. Okay, so in this case here, what is a pivoting element? This is a pivoting element. 1 minus 1 over 1.2, and then what you have here is you got Kp minus 1. Okay, 1.2. So right, Kp minus 1.2. So this is actually equal to 1 over 1.2 or 1.2 minus Kp. Okay, and then of course the last one is just going to be Kp. So what do we ask to test? We are asked to test Kp is equal to 1, Kp is equal to 0.5. Okay, so from this requirement here, we know that Kp for stability, right? For stability, if you were to look at your stability from here, you know first Kp has to be greater than 0. And then the other one, Kp has to be less than 1. Kp has to be less than 1.2, because when Kp is less than 1.2, this element will be positive, right? Because this element here is 1 over 1.2, it doesn't matter, it's just a factor. Inside here is 1.2 minus Kp. So you want this to be positive, right? Because 1 to 1.2, 0 sign change. 1.2 to the next one, you have a sign change. If Kp is actually less than, more than 1.2. If Kp is less than 1.2, positive, 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 okay. No sign change, system will be, closed loop system will be stable. Okay? Nevertheless, if Kp is greater than 1.2, you're going to have a problem. So we do know that Kp is going to be greater than 0, less than 1.2. Okay? So you are given 2 to test, straightforward, right? Okay? You're given this 2 to test. I mean, can work out the answer. You do know, right? Kp is equal to 1, closed loop system will be stable. Kp is equal to 1.5, because it's greater than 1.2, closed loop system will be unstable. Okay? Alright? Any question? No question. Good. Good or bad? Good. Okay, because no question, it can be good, it can be bad, right? No question, fully understood. Very, very good. No question, do not know where I don't understand. That is not so good. Okay. But as I mentioned to your guys, you are already in year 3, year 4 of a 4-year degree program. So it is actually perfectly alright. Even if you read it before you come to class, you sit through the class, you understand 40-50%. It's alright. This is not a primary school, right? Primary school, you go in, wow, you expect to know everything, even up to P6, right? Sometimes, you know, I mean, secondary school, yeah, sometimes you also, some things you understand, but some things you don't understand. But come to university, basically, this is something that everyone has to accept it. I went through the same thing with your guys, right? 20, 30 years ago, I was in the same situation like you guys, going through all this. First time you listen, the guy teach you. I mean, but maybe you understand 30-40%. You go back, you revise, you read, and then you practice. And then from there you learn. Okay? I mean, basically, like what we said, right? Practice makes perfect, and so on and so forth. So that is why you need to practice. You don't expect you sit through. I mean, there are a few of your guys, I do know that extremely intelligent, sit through 2 hours, understand 100%, that will be very good. Okay, those are maybe 5% of the cohort. So don't worry, 95% of the cohort, all of us in the same shoe, in the same boat. You sit through it, you understand 30-40%, good enough. The basic thing is you understand the basic, you go back, you practice, you fill out the rest of the 70%. Okay? Alright, so don't feel discouraged. Oh, I don't know what he's talking about.
Is singlet cheaper than a shirt?
No, everyone in the same boat. Okay? The important thing is you help each other, you try to revise each other, try to basically find out which one you don't understand.
Probably is from the same company.
Alright, let's take a look of PD controller for a second order system. We mentioned just now, right? We mentioned the PD controller, so remember what I mentioned. So all you need to remember are basically the summary of the key characteristic of your PID. And then after that, you apply to any other system. You see that I will only be using the same analysis and then basically the same approach. It's not going to deviate anything from there. Okay, so coming to this closed loop second order transfer function with the PD controller, we mentioned P, what you're trying to do, speed up the response, reducing the steady state error. E, basically improve relative stability. Okay, so that is the most important thing that we mentioned for your PD controller. So this will just be the same, standard procedures that you need to do it. I work out the transfer function and all that, but primarily that is also for you, as I mentioned many times, for you to practice. What is a CS over RS? ES over RS. So you can see that it's actually quite mundane in the sense that we need to go through it, but don't feel it is actually mundane, because what happened is, I guarantee you, by the time come to exam, there will be students looking at this, will not be able to produce the closed loop transfer function. Okay, so if you want to practice now, you take exam to the first time you practice, you're going to see, you're going to face with a lot of difficulty. So this is a good time, basically, for you to practice, to find out where you actually make mistake. Okay, so this is a closed loop transfer function from RS to CS. This is a transfer function from your reference input to your actuating error signal. Okay, and then from this, you can actually see, looking at these two terms here, you can actually work it out. Again, omega n basically doesn't show up. The DC gain for this is going to be equal to KP plus KP over KP plus 1, because this term actually disappeared. Right? This term basically disappeared because in your DC gain calculation, KDS actually disappeared. So it's going to be KP over KP plus 1. And that's what you see, KP over KP plus 1. Alright? So steady state error 1 over KP plus 1. Alright? Okay. Now coming back, these are the things that we are interested in. Characteristic equation of the closed loop system. So if you were to go back and to say that, okay, in my closed loop characteristic equation, I go back and write it in this format. S squared plus 2 zeta closed loop omega n closed loop S plus omega n closed loop squared equal to 0. Because it's still maintained from the transfer function. You can see it is still maintained as a second order transfer function. But what we are trying to do is we're trying to see how the undamped natural frequency damping ratio have changed. Right? These two parameters, how have they changed when you close the loop? So in this case here, if you were to see that, you can see your closed loop, your omega n. So what happens to your omega n? You can see that closed loop omega n is going to be larger than your open loop omega n, right? Because omega n closed loop is omega n multiplied by square root of kp plus 1. Then what about your damping? Damping in a way, if without the kd term. Okay, so guys, listen. If you were to take a look here, if without the kd term, that means this term is missing. What happened to your closed loop damping? Your closed loop damping is just going to be, so if you were to take a look, your closed loop damping, your zeta closed CL is going to be equal to 1 divided by, so it's going to be equal to zeta multiplied by Kp plus 1. Okay? So this is your closed loop damping. So zeta is your open loop damping. So what can we say about your closed loop damping if we do not have the KD term? By looking at this, we do know that your square root of Kp plus 1 is always greater than 0. Okay? And you can also imply that square root of Kp plus 1 will always be greater than 1, correct? Because it's a square root of Kp plus 1. So Kp is equal to 1, square root of 2 greater than 1. Kp is equal to 2, square root of 3 greater than 1. So this is always the case. And if this is always greater than 1, so what happens? Your zeta closed loop will always be less than zeta, correct? Okay? And that is why you will see that if I have to close the loop using just a P controller, it is actually not very good because I'm just using a P controller. What happens now is my closed loop system will have a damping that is actually smaller than my open loop system. Okay, and that is why when you go to your PD control, okay, when you go to your PD control, this is what you will get. You have zeta plus half of KD omega n. Okay, KD omega n. So this KD is going to provide you the extra damping that you need. So if you need to improve on the damping, like the example just now we have seen, zeta is equal to 0.2. So now you can actually use a KD term to actually increase your damping to a level that you are typically more comfortable. So a level that we are typically more comfortable will be somewhere around 0.4 to 0.8. Okay, in your design. But because you're not doing design, so but you need to remember some of this figure. So zeta typically you work with 0.4 to 0.8 because you do not want your damping to be too high. So 0.4 to 0.8 will be a nice number to work with. Okay, PD control introduce an offset error, as we have seen, steady state error. Proportional action increases the natural frequency, closed loop and then natural frequency, and derivative action increases damping. Okay, the derivative action actually increase the damping as what you have seen in this example here. Okay, this analysis, you basically, as what we have mentioned before, the objective is to increase the damping of your closed loop system and in a way improving your relative stability. So this is basically again is for you to practice. I mean, if you were to ask me whether you're required to do this in exam, some exam, yes, they did ask you to work out what is a closed loop step response and so on. So you need to actually reproduce, but I believe you cannot actually just do it this way because this is a very generic form of just deriving it. So what you need to do is you base on a problem, you work out from the transfer function, and then you do an inverse Laplace transform. When you set your Rs is equal to 1 over S, and then you do an inverse Laplace transform, and then you work out the two terms, right? E to the power of alpha t, and then also your zeta omega n and so on. This omega d term. Okay, so you actually have two terms. So you have this term basically controlling your decaying exponential. So this is a decaying exponential. This is basically your oscillatory frequency. Okay, so you can actually see that closed loop then natural frequency omega d close CL is going to be equal to omega n CL multiplied by square root of 1 minus zeta CL squared. So that is primarily using the equation just to work it out. But you need not always trying to identify them. But if you need, if there is number provided, it can actually be identified quite straightforward. Okay, it should not be too much of a problem. Let's take a look of this example here. Okay, in this example here, you can see that zeta is equal to 0.2, omega n is actually equal to 5 radian per second. And then what happened here is this is the original response, right? Because it's go to 1, and then open loop, and then this basically PD. So this is a case where you set your Kp is equal to 1, your Kd is equal to 0.1. Okay, you set your Kp is equal to 1, Kd is equal to 0.1, and if you were to work it out, okay, you work it out, what is your closed loop and then natural frequency? 7.07. What about your closed loop damping? 0.2. 0.32. Okay, and what happened now? You can actually see that your steady state error is 0.5. Okay, you do have steady state error. Okay, so important thing you remember, if we were to play around with this KP and KD, you can actually see that the closed loop damping has actually improved. So open loop system, you can see is quite oscillatory. When you close the loop, it is not so oscillatory because why? Because the damping has actually improved a little bit. Okay, so if we were to take a look, so this one is actually additional. Okay, if we were to take a look with this PD controller, okay, so this one is not in your notes. This one is additional information given to you. Okay, additional information given to you is up to you. You want to pick it up, you can pick it up. If you think it's too much, then if you don't want to pick it up, I don't know. But these are things that I always cover with the students, so I think it's actually useful information. Okay, but if you think you don't need extra, this is also okay. But what I'm trying to point it out to you, if you are to take a look of your closed loop transfer function, just now I've actually shown you this closed loop transfer function. I can actually rewrite this as this transfer function. Alright? What I'm trying to point it out to you is you actually have a 0 in your closed loop transfer function. And one of the things that we will talk about, maybe in your root locus and all this and that, is you will realize that anytime when you place a PD controller in your forward loop, what happens? When you place a PD controller in your forward loop, you are placing a 0 in the forward loop. Okay? We do mention that the whole idea of your closed loop transfer function is to tweak your pole location. Okay? One of the key things that we say that, okay, when you design your feedback controller, you are designing it to tweak the closed loop pole location to a location that you are comfortable with. You want the system to have that kind of behavior. Okay? So closed loop feedback primarily will change your closed loop pole location. But what about your 0? 0 is something that unfortunately you cannot change. Okay? You cannot change. You will realize you can go and practice 10 times, 1,000 times. You will see that if I place a 0 in the forward loop, when I close the loop, that 0 stay put at that location. Okay, so what I'm trying to tell you here is, if you were to place this 0, the moment you place a 0, this 0 will always stay put in that location. And here, what I'm trying to relate is the 0 basically relying on your KP and your KD value. Okay, this 0 location, right? Because I'm rewriting this whole transfer function based on the numerator polynomial. So if I have to factor out, in this case here, if I have to factor out a KD, I can actually have your Z is actually equal to KP divided by KD. So that means by carefully selecting KP and KD value, I dictate the closed loop 0 location. Okay, the 0 location can actually be tweaked. So if KD is actually a very small value, then KP is a large value, then you have a 0 that is actually very far out into the left half plane. If KD is a large value, KP is a very small value, then your 0 is actually very close to the j omega axis. Alright? Okay, basically just that. Okay? And here what we are trying to say is, as a result, if you were to take a look in your Z selection, you will see that 1 over Z is actually KD divided by KP. So if you have a very, very small KD value, and then you have a very large KD value, you can actually see that the effect can actually be quite different, right? When you're trying to place around your 0 location. Okay, so here we do realize that, okay, 1 over Z is KD divided by KP. So here we are trying to go back to this unit step closed loop response. Okay, so you will see that this is basically in your unit step closed loop response. Let me see here. Here doesn't really show it. Okay, this is a term. Okay, you can actually see this term showing out here. Okay, this term KD divided by KP. So this term KD over KP actually has certain effect. Okay, so this basically just to show you how this actually coming about. So this KD over KP is 1 over Z is actually in one of the inverse Laplace transform in your CP. Okay, so we do know that this term can actually affect your step response because this is a step response where you set your RS is equal to 1 over S. Okay, so now what we are trying to show you is if the 0 is actually near the closed loop pole, when you place your 0 location, as we mentioned, 0 will always stay put, it will not move. 0 is very near the closed loop pole, transient response becomes considerably different from that of a second order system without a 0. Okay, so what we are saying here is if you were to go back, look at this. Okay, so this is my closed loop pole location. So as we mentioned, when you put an open loop 0, the 0 will stay put. So if I put a 0 somewhere around here, basically I'm saying that this 0 is basically close to the closed loop pole. I'm actually measuring based on what? Measuring based on the relative real part of your complex conjugate pole. In this case here, I'm actually basically measured based on the zeta omega n of this pair of your complex conjugate pole. So I'm actually looking at the 0 location and also looking at your zeta omega n. Okay, ideally you want this 0 to be as far out as possible. Okay, you don't want the 0 to be here, around this region. Okay, we typically do not want the 0 to be around that region, right? Close to your closed loop pole and also close to your j omega axis. Okay, why? Because the reason very simple. If you come back, you can actually see that. You can see the 0 is close to j omega axis. The effect of the 0 on the unit step response will be very significant. In what way? So this is what we actually plotted out. Okay, I plotted out this. Omega n is equal to 2. Zeta is equal to 0.707. A very high damping. The solid line basically represents the system, second order system without a 0. That means it's just a pure second order transfer function, closed loop. And then now I place a 0, where 0 is going to be equal to the location of zeta omega n. So when 0 is equal to zeta omega n, that means the 0 is actually aligned with your closed loop pole. So if you go back to this diagram here, it's basically a line, one straight line. So it is a case, the second diagram that you have seen is a case of your 0 is actually located here. So it's actually a one straight line. So 0, in this case here, your 0 is actually equal to zeta omega n. Okay, so you can actually see that when that is the case, when 0 is actually aligned the same direction, what happened now is if you were to take a look, you actually have a higher overshoot. Okay, you have a higher overshoot. Good thing, response is very fast. Good thing, the response is very fast, but you do have a higher overshoot because why? Because now your closed loop system has a damping of 0.707. Right, or higher damping. But nevertheless, when you were to take a look of your response doesn't look like a system with a damping of so high. Because why? Because the overshoot is higher. And if I have to shift the 0 even closer, okay, so this is a case where if I shift the 0 even closer to the j omega axis, half the distance. So if 0 is actually equal to half of zeta omega n. Right? Closer to the j omega axis than your complex conjugate pole, and you see what happened. The response has very high overshoot, 70%. So that is something that you have to be very careful. So when you place a 0, when you use a PD controller, yes, we do mention that PD controller actually help you to improve your response and all that, relative stability and all that. But at the same time, this is something that you have to be very careful. Okay? But one key thing that you also realize from this analysis is if you were to take a look, whatever high response, fast response, high overshoot and all that, all this happens only during the transient. As what we always say, your PD controller, your D controller has no effect beyond the transient. it's only during the transient it has effect, right? We mentioned in your D controller, we mentioned many times, your D controller is good because it has anticipatory effect, improve your relative stability. But all this effect only comes in during the transient. So you can actually see that during the transient, the moment it hits steady state, no more effect. Okay, the effect actually disappeared, diminished. Okay, the effect diminishes after the transient has actually decayed. Alright, so these are things that is something that is good to remember, because in your design, when you use a PD, you also must be mindful that, because you see, if you're not asked to do a design, you're not asked to analyze a response and so on, so sometimes you might not need to. But if you're asked to analyze a response, so this will be something that you need to take note. Okay? Alright. Okay, let's take a look at this work example 2. This work example 2, you have an angular output of a servo mechanism data. It's actually controlled as indicated in the figure below. I'm not too sure whether you have this servo mechanism, and then you have a controller G1. And then what happened here is your reference input is your reference angle. And then you have this angle that you're trying to control through your servo mechanism. Okay, let's take a look. And okay, so displacement. So you are trying to control angular displacement data. You have a reference displacement. The controller transfer function is given by G1S. The torque it applies to the servo mechanism is denoted by TS. And then the error signal is actually ES. Right? So this is a torque applying to your servo mechanism to actually give out the angular displacement. And this is the actuating error signal. This is a controller. Okay, we are asked to calculate the damping and natural frequency of the uncontrolled open loop system. What is the maximum overshoot of the uncontrolled system in response to a unit step change in torque TS? Okay, so these are some of the things that we were asked to do. So we have this uncontrolled open loop system that we need to actually deal with. So the uncontrolled open loop system, part A, we'll ask this, and then we'll ask of the uncontrolled open loop system, what is the maximum overshoot of the uncontrolled system in response to a unit step change in torque? Okay, so what happened here is you were asked to find out what is the maximum overshoot. So if you work out the damping, right, you can actually work out your maximum overshoot. So this is basically given in your notes.
e to the power of minus zeta omega n Tp. Okay, so you need to actually work out what is a Tp. Tp is your peak time, is equal to pi divided by omega d. What is omega d? Omega d is equal to omega n multiplied by square root of 1 minus zeta squared. Okay, there is another formula. Let me see, see whether I can remember. Mp is equal to e to the power of minus zeta divided by 1 minus zeta squared. This one is not given to you, but this is actually you'll find in the textbook. Okay, so in the way I mentioned to you guys before, your overshoot, maximum overshoot relates directly to your damping ratio. It's 1 to 1. You know one, you know the other. You know the other, you know the other one. So if you are given maximum overshoot, you can work out what is the damping ratio. You know what is the damping ratio, you can actually work out your maximum overshoot. Okay?
You multiply a pi on the second equation.
Okay.
To the power.
Let's see, what's the next thing we need to do? Proportional control, we gain Kp is equal to 10 is applied. Calculate the closed loop natural frequency and damping. What is the steady state error in response to unit step input in data RS? Calculate the resulting maximum overshoot. Right? Okay, this is what you see in exam. Alright? So that is why I said you need to practice. It is doable, straightforward, not difficult, but tedious. But hey, you have 3 hours, right? Or else you're going to be falling asleep. Okay, you have 3 hours there, you know. 5 questions, 3 hours. Don't do anything, I guarantee you will fall asleep. If I have to invigilate, I will also fall asleep. Okay, so now we're looking at this. Kp divided by s squared plus 4s plus 10. Okay, so we need to work out. So this is a case of your data Rs. I mean, you can actually just, so this is your Es. I can actually call this Rs over data S. Okay, what is your closed loop transfer function? Data S over Rs. Closed loop transfer function is going to be equal to Kp divided by S squared plus 4S plus 10 plus Kp. Okay, proportional control with again Kp is 10 equal to 10 is applied. Calculate the closed loop natural frequency and damping. What's the steady state error in response to a unit step input in, okay, so question basically this already called it data Rs. Okay, calculate the resulting maximum overshoots and so on. So what happened here is from this, what is your closed loop damping and your closed loop undamped natural frequency. So this is your omega n closed loop squared is equal to 10 plus Kp. Okay, and then your 2 zeta closed loop omega n closed loop is equal to 4. So it's still the same. Zeta closed loop is going to be equal to 2 divided by omega n closed loop. Okay, so I'll leave it to you to work it out you roughly you know, right? And then from there, okay, so this, when you work it out, this will be physical value. Okay, now they ask you what is the steady state error in response to a unit step input in your data reference. So from this case here, what is your DC gain? DC gain is Kp divided by 10 plus Kp. Right? Kp is equal to 10, this is equal to half. So steady state error is 0.5, correct? Okay, agree? Steady state error is 0.5 because your DC gain is equal to half. That means if your data Rs is equal to 1 over S, your data Ss is equal to half. As a result, your ESS is equal to half. Okay? Alright? And then they ask you to calculate the resulting maximum overshoot. So all you need to do is your maximum overshoot is going to be equal to e to the power of minus zeta closed loop divided by square root of 1 minus zeta closed loop squared. What? Okay. Ah, correct. Your friend. Very good. At least someone thinking. Oh, so now there's a pi missing. Correct? Oh, that's A1 and A2 different. Okay, thank you. Okay, so the formula for MP is equal to e to the power minus pi
John
zeta
Lun knew it
divided
before
by
everybody.
square root of 1 minus zeta squared. There is a pi.
Scholar Lun.
Right? Thanks to your friend pointed out. There is a pi there.
Yeah,
Okay,
John
so
Lun know
if
it
you
long
want to use
ago.
my formula, there's a pi, so it's e to the power minus pi zeta closed loop divided by square root of 1 minus zeta closed loop squared. Okay, there is this this pi missing. Okay, very good, very good. I like it. Or at least you're paying attention and following the okay, now the rest of you, there is a pi missing. Just now when I wrote it, there is a pi missing. So you need to actually add this pi here. So e to the power minus pi zeta divided by square root of these are the exponent. The exponent is e to the power minus pi zeta divided by square root of 1 minus zeta squared. Okay? Alright? Okay, so this will be part 2. So calculating the resulting maximum overshoot, I leave it to you to do it. Okay. Then we come back, we quickly see what do we need to do. Okay, the last portion of it, derivative action with gain KD is equal to 4 is now added to the proportionate action. Calculate the closed loop natural frequency and damping. What is the steady state error in response to a unit step input? Okay, in data RS, calculate the resulting maximum overshoot. Okay, so you are given all the information is already given to you. KD equals to 4. So what you need to do for this, basically will be to go back to work out what will be the closed loop transfer function. So we need to work out with the PD controller. So now with the PD controller, Kp plus KDS. So this is my original S squared plus 4S plus 10. So this is data RS, this is your data S, and this is an ES. Okay, so with this, all I can say is your data S over data RS. So this will be your closed loop transfer function Kp plus KDS. Okay, so this is what I mentioned to you guys. You will see that in the closed loop transfer function, okay, this term will basically show up as squared plus 4s plus 10 plus kp plus kds. Okay. With the parameter given, kp is equal to 10, kd is equal to 4, I can actually rewrite this. Basically, it's going to be 4s plus 10 s squared plus 8s, right? Plus 20. Okay. Again, what is the DC gain of this system? DC gain is still equal to half. So steady state error, ESS, is still going to be equal to half, correct? When you have a step input. So these are things that cannot change. Okay, cannot change. And then now if you try to find out what is the closed loop characteristic equation, CLCE is going to be equal to s squared plus 8s plus 20 is going to be equal to s squared plus 2 zeta closed loop omega n closed loop s plus omega n closed loop squared is equal to 0. So your omega n closed loop squared is equal to 20. And then now your zeta closed loop omega n closed loop is going to be equal to 4. So this one, you have your omega n closed loop is equal to square root of 20. So your zeta closed loop is going to be equal to 4 divided by square root of 20. Okay, so it's basically 2 divided by square root of 5. Okay, alright. So you have all this. What is about your maximum overshoot? Maximum overshoot e to the power minus pi zeta closed loop divided by 1 square root of 1 minus zeta closed loop squared. And this will be your MP. Okay? Alright. Okay? Don't just write this, go back, fill out the numbers, work out the numbers. Because this is what you're going to be asked to do in the exam. Right? A lot of times, basically, they give you all this, but basically, this is what you need from closed loop transfer function. From the closed loop transfer function, you work it out. So, accept that, what they're going to see, what you're going to see in the exam, most likely is they will not tell you that Kp is equal to 10, Kd is equal to 4. But they will tell you that this is what I want to get for my maximum overshoot. Okay? And this is what I want to get for my undamped natural frequency. And you tell me what is my Kp value, what is my Kd value. So you actually need to work backward. So as we mentioned, if you were given maximum overshoot, straightforward, you can actually work backward to get your undamped natural frequency. And then from there, you say, okay, this is my 2 zeta closed loop omega n closed loop is the first order term. From there, you can actually see that how you can actually try to work backward to find out what is your undamped closed loop natural frequency, omega n CL. And then from there, you will see from all the set of the transfer function here, alright, hopefully from the closed loop transfer function here, I can actually try to pinpoint what will be the Kp value, what will be the Kd value. Okay? Alright? Okay, so can you work backward? If you are given undamped natural frequency, you are given damping ratio, and then you work backward to try to find out what will be your closed loop Kp and Kd. So this will be something that most likely sometimes it tests you in the exam. Okay, not always they give you the number. They will always like to work backward to find out. So they can actually say that, okay, now I want my steady state error to be 0.2. Then what is my Kp value? So you do know that your Kp basically relate to your steady state error. So if you have a ESS of 0.2, you most likely can work out and straight away you can actually link your Kp value. Okay? So that will be something that we will basically look into. Okay, all right, let's carry on. Let's take a look. So now we are looking at what we call integral control action. As we mentioned before, your integral control action is useful, right, in eliminating. Okay, what is the integral control action you want it to do? You want it to use it to eliminate your steady state error, right? Because we do see that using your P controller, you can minimize your steady state error. But we also see that when you try to minimize your steady state error, you cannot eliminate your steady state error. So steady state error can only be eliminated using your I control, integral control. Okay, so important thing, integral control eliminates steady state error, at the same time can also regulate your disturbance. If your system has a disturbance, disturbance can actually be attenuated or can be minimized through an I control. Okay, so but typically when you use your I control, I can tell you that you need to use it with care. But because you're not asked to do design and all that, so maybe perhaps you know some of the things they already fix it, the form and all that. But typically when you use your I control, you have to be very careful because of the effect that you can actually destabilize the system. So maybe we will take a look. Alright? So in this case here, this is a first order system. If you look at your closed loop transfer function, why I say that you actually eliminate your steady state error? Because if you were to look at your closed loop transfer function, same thing that we have gone through. First thing you realize your DC gain is equal to 1. DC gain equal to 1, typically no steady state error. Because why? Input is 1, output is 1 at steady state. So where is the error? No error. So that is a very clear indication. And that is why I say using a DC gauge is very fast. Straight away I look at it, I can tell you that there's no steady state error. I don't even have to do all this, all the steps and all that. You can basically, in exam, if you were to look at this, you say DC gain is equal to 1, no steady state error, no marks will be deducted. Okay, alright? So these are basically a very quick approach, or else you're going to have to do all this. Okay, you need to carry out all this if you do not want to use the other approach. Okay, and then from here, we conclude your ESS is equal to 0, as what we mentioned. Okay, we conclude ESS is equal to 0. Okay, now coming to the effect of your integral control on response of a first order system. Okay, as you can see, your integral control removes your offset, steady state error, but at the same time increase the order of the system by 1, and that is what I mentioned. And that is sometimes it can be a problem. Okay, in this case here, you increase the order by 1, and you also place a pole at the origin. Right? You place a pole at the origin. Nevertheless, the moment you close the loop, the pole might not be at the origin. Okay, so that's not so bad. But depending upon the gain K value that you're using, okay, and some other things you have more effect. Okay, so now what happened here is your closed loop system can be a second order system. Because why? Because originally first order, use the integral control, it becomes a second order. Closed loop is a second order transfer function, and then you can actually look at second order characteristic equation. So it all depends. Because why? Because it depends on the gain K value that you are using for your integral control Ki. If Ki is a small value, you actually get 2 real roots on the real axis. It can be a situation because what happened here is your original system is the first order. When you close the loop, so this is sigma, zeta, omega n. So original system, basically you have minus 1 over tau, alright? So that's your pole location. Now you place a pole at the origin. So when your gain K is actually very small, your pole can basically, closed loop pole can basically either K becomes very large, you actually have a complex conjugate closed loop hole. Okay, so those instances that you have seen here pretty much correlate to when your gain K is fairly large value. Okay, so what happened here is we try to do some comparison. Okay, we try to do some comparison. Comparing with denominator of the transfer function, you can actually work it out based on the denominator polynomial. Right? You can actually work it out what will be your omega n closed loop and then what is your zeta closed loop. Okay, so all this basically you can actually work it out. Because why? Because when you have your overdamped situation, zeta is greater than 1. Zeta closed loop greater than 1 can also be represented using that transfer function. Right? Overdamped situation as what I showed you all here. Right? That's what I showed you all here. If your pole is still on the real axis, your zeta closed loop will be greater than 1. Okay, but you can still actually try to work it out. But nevertheless, that is actually a situation of two real roots. This is basically pure complex conjugate situation. Okay, all right. So you can see this is a case where your time constant is 1 second. Okay, so now I set a Ki to be 20. So when I set a Ki to be 20, what happened? My closed loop undamped natural frequency is 4.47. And my closed loop damping, what happened, is 0.1118. And that is why you see the closed loop response. What happened to the closed loop response? Very oscillatory. Why? Because the damping is only 0.11. Okay? Whereas the other scenario where I pointed out to you, when you have your Ki to be a small value, when Ki is a very small value, you are basically overdamped situation. You can actually see that when Ki is equal to 0.2, what happened to your undamped natural frequency? Small. What is the damping? Damping is greater than 1. Because why? Overdamped. Right? When you have an overdamped, you have two real unequal roots on the real axis. And if you have to look at the response not so good. Okay? Because this is a case where your damping is actually very high. Right? When your damping is very high, basically is what we call a very sluggish response. Right? Because the response is very slow. It will still give you zero steady state error, regardless of what kind of Ki value that you're using. The good thing is the moment you use an integral control, you get a zero steady state error. Except that the response is going to be very sluggish and all that. So that basically, as what I always mention, right? You can use this door and then you can play around with it. If you're allowed to play around, you tune the damper. This is a case where you tune the damper, it is very high. What happens? You open a door, it takes about 15 minutes to close. Okay, so this basically, the last one correlates to, you open up the door, you let go, you're having lesson inside here, the door will take about good 5-10 minutes to close. And that is basically what we call a very sluggish response. It takes a very long time for a system to respond to the input. Whereas this one, you know, the door is going to slam because the moment you let go, pump, this guy's come back very far. And then you overshoot. Okay, except that of course your door, you cannot have the door swing inside, so it will just hit the door frame and it will just give you a loud bang. Alright? But typically what you see here is you have a situation where your damping is actually very very small. You have very high overshoot. You have what you call 60-70% overshoot. So typically in your feedback control system design, this is undesirable. Undesirable because if you were to imagine your structure is going to be subjected to such a high overshoot, can your structure actually take it? So you can actually imagine that if your wing is going to go through such a high fluctuation, when you hit the turbulence, can your wing actually withstand such a high fluctuation? Right? Your final value is here, then you go out 60-70% of your overshoot and all that. So it is something that certain things, yes, you design for it, but certain things, if you're not designed for it, it will fail, right? Structurally, it's going to fail. Okay? Alright. Okay, let's take a look of this again with the second order system. So we have seen first order. Let's take a look of your second order system now. So in the second order system, what happened here is you have a closed loop system. second order system with the I controller. So the good thing in your first order system is you do not run into stability issues. Okay, I mean it's a bit difficult for me to explain to you, but when we go into root locus, I can actually illustrate to you why I say that. First order system, you'll not run into stability issue as long as you're using a time domain analysis. If you're using frequency analysis, yes, system can actually be destabilized, right? But in the applying to a second order system, that is very real. That you will see that if you're not careful with tuning your Ki value, you do run into instability situation. So this is your closed loop transfer function. So again, if you were to take a look now with your integral control, what is your DC gain for this system? Again, the DC gain is Ki omega n squared divided by Ki omega n squared equal to 1. That's what we have promised, right? Integral control action eliminates steady state error. So you will not see any steady state error. And if you were to apply your final value theorem, your CSS is equal to 1. So your ESS is going to be equal to 0. Okay? So very straightforward, standard clear-cut type of result expected, because we know the whole idea of using that that's what we're going to be doing. Okay? So in a way, so I'm basically following the Glasgow, so I didn't add anything in for your. So, but if you want, you can actually, what you need to try to do is you take the closed loop transfer function, because what happened, why I didn't actually do extra work for you, is in a way, now this is a third order. Okay, this is a third order transfer function. So as we mentioned, you need to actually factorize it into a first and a second order. So if you were to take the third order transfer function, if you were to factorize, you can actually get two scenarios. One, you can factorize into 3 first order, or you can actually factorize into a pair of complex conjugate, 1 second order and 1 first order. Am I correct? Right? It's either 3 first order or 1 second order and 1 first order. So that is why, I mean, we don't really analyze it further, because we basically base on, as I mentioned to you, okay, anything that is higher order will be based on the technique that you have learned, you have picked it out for first and second order. Okay, so you need to have a little bit more information before we can actually analyze that. So typically what you can do with this is you can actually try to analyze stability. Okay, one thing you can do is actually try to do stability. So I will ask you to try to do the stability. Next lesson you come back, we will discuss what happened to the stability. Can we always guarantee stable third order system? Right? In this case here, under what circumstances you actually ended up with a situation where your closed loop system becoming unstable using your integral control, right? As much as we want to eliminate steady state error, we do realize that it can actually lead us to instability. Okay? Alright, so this is basically another one is if you use a PI control and you're applying it to a first order system. So again, your PI control add your system order by 1. So first order system become a second order system. But nevertheless, if you were to go back, do the same analysis, you will realize that if we were to look at the DC gain, Ki divided by Ki, again, a situation where you get 0 DC gain. I mean, 0 steady state error, the DC gain of 1. So your steady state value CSS is equal to 1. Okay? Alright, so if you were to follow such analysis, this will always be true. Except that, of course, now you can, based on this result, you can actually have either 2 first order or a second order complex conjugate pole. Okay, because why? Now the transfer function is actually a second order transfer function. So a second order transfer function, it can be either 2 first order or a second order. Second order meaning is actually under them complex conjugate poles. Okay, in the complex S plane. Okay, so now we see that integral control removes your offset steady state error but increases the order of the system by 1. So integral action affects natural frequency, you can actually see from the closed loop characteristic equation, we can actually work it out how the undamped natural frequency for closed loop is going to be affected. So if you have a very high Ki value, you can actually have a very large closed loop undamped natural frequency. But at the same time also, when you move your system into the complex plane, you have your damping ratio. That is actually less than 1. Because if you still remember, when we talk about your damping ratio, okay, when we talk about your damping ratio, do you remember that the damping ratio, the measurement is basically from your what? Is from your negative real axis. Cosine theta is going to be equal to your zeta. Alright? On the negative real axis, your zeta is equal to 1. When you go to j omega axis, because it's 90 degree, cosine 90 degree is equal to 0. So on the j omega axis, what happened? Damping is equal to 0. Okay? That is why we say that when you have a pair of complex conjugate poles on the j omega axis, your system has no damping. Remember that? Okay? We mentioned that before. And this is basically, you can actually try to compare. Okay, so this will be a situation where you can actually compare playing around with your Kp and then also playing around with your Ki value to see what kind of damping that you will be getting. Okay, very quickly, let's take a look comparing with denominator of transfer function. So we are given a situation where your open loop time constant is 1 second, integral control Ki is equal to 10, and then your undamped natural closed loop in a way now is 3.16. Your closed loop damping is 0.15. Okay, so this is only with the pure integral control. With the pure integral control, this is the case. But if you were to use your PI control, what happened now is you have a Kp of 3, Ki of 10. So if you were to compare your undamped natural frequency, they are still the same, 3.162. Except that now, with the PI, you can actually see that what happened to my damping? My damping can actually be rather large. And that is the effect that we have seen from this exercise here. Using a pure integral control action, eliminates steady state error, but at the same time, you don't have much control. Sometimes if your Ki is actually a large value, your damping becomes very small. But if you have a P controller or P control action, you can actually try to maintain your damping. So now the damping is what? 0.6, quite a reasonable figure. So in this case here, what I'm trying to show you is this is a case where you have a pole, S is actually at -2 plus minus J 2.45. Where is your 0? Your 0 is basically at S is equal to minus 3.333. Okay, this is correct. Yeah. Is this correct? Yeah. It is because you see what happened. We mentioned earlier on we talk about your PD. PD straight you place a 0. If you use a PI controller, we mentioned I controller increase the order by 1, place a pole at the origin. When you use a PI controller, if you were to combine this, what happened? You place a pole at the origin, you also place a 0. Okay, so that is what I'm trying to show you in this. So this is actually slightly different from, I think in your lecture materials they don't put this in. I added this in primarily is to show you that what happened now is you have a pole at -2 plus minus J 2.45. You have a 0 at minus 3.333, which is actually rather close to your pole at -2. If you were to look at only the real part, and that is why if you were to look at the response, so this is a response of a PI controller. If you were to look at a response of this PI controller, the integral controller, because the damping is 0.15, so the overshoot is rather high, right? You have a rather high overshoot of about 70%. Now, increase the damping to 0.63. Overshoot should be about 10%, but I'm still seeing a 25%, right? The maximum point is somewhere around here. So I'm still seeing about a 20-25% overshoot. Why is that so? And that is why I give you this two number is basically to show you that. Why? Because the 0 is still rather close to your JO, the pole, your complex conjugate pole. Okay? The 0 now is to the left of your complex conjugate pole. Though it's to the left of your complex conjugate pole, it is still giving you some effect of what we discussed earlier on. Okay? We discussed earlier on, when you have a 0, right, on the real axis, your system response can actually be quite different in a way that the 0 has the tendency of increasing your maximum overshoot and at the same time speed up the response. Very short rise time. So it is actually very good. Okay? Because what happens is you do realize that when you have a small damping, key characteristic of having a small damping is the response is very fast. Your response is what we call very crisp, very fast. But when you increase the damping, you will see that your response gets slower and slower. So if you were to compare this system with the damping of 0.158 with the system with a damping of 0.63, you expect the system with a damping of 0.156 to be much faster. But this is not what you have seen here. If you were to take a look here, this is a damping of 0.158 and this is a damping of 0.63. And if you were to compare these two, you can actually see very clearly that the system with the damping of 0.632 actually responded faster. And the reason why is the reason so? Because you have the 0. You actually have the 0, which is actually near your j omega axis. Okay? And that's why we are seeing such a fast response. Okay, I think we will stop here because I don't think we have the time to go through this example, but do read ahead, take a look of this work example because there's a couple of things that you need to do. There are 5 items that you need to work it out for the work example. Okay, so I think we will stop here and I'll continue next week. Next week is still a studying week, it's not Chinese New Year week. Okay, no doubt next week is going to have your Chinese New Year, but you still need to come
next
to
year.
class.
Next week. Is it Chinese New Year?
Okay, alright, so I'll see you all next week.
Yeah, that's right.